Picture this. You're adrift in the vast expanse of space. Before you looms a black hole, an abyss so deep, so utterly devoid of light, it feels like the universe's darkest secret. Silence reigns, an eerie stillness that stretches into infinity. Not a whisper escapes, not even the faintest glimmer of light dares to return. Now consider this, the waiting, not mere seconds, not even years, but an eternity that eclipses the very age of the universe. And then, the revelation. Stephen Hawking unveiled a shocking truth. If the principles of quantum physics hold true, that black hole is not eternal. It will gradually shed its energy, shrinking into nothingness. And one fateful day, it will vanish. Can you feel the tension? The thrill of the unknown? In the vastness of space, even the darkest mysteries are destined to unravel. In the wild world of classical physics, black holes are like the ultimate cosmic vacuum cleaners, absolute and all-consuming. Imagine this. The event horizon, the point of no return, is like a cosmic do not enter sign. Step across it, and every possible future path you might have taken zooms inward, like a roller coaster plunging into the abyss. From the outside, anything that dares to cross that line is gone for good. Poof! Disappeared into the mysterious void. In this cosmic drama, black holes play the role of the perfect thieves. They gobble up everything in sight, but never return a single crumb. They're the ultimate party crashers of the universe, always taking, never giving back. In the enigmatic realm of quantum physics, empty space transforms into a theater of the extraordinary. What we perceive as a void is anything but. It's a pulsating canvas of potential. Even in its most subdued state, the vacuum is alive with whispers of energy. Quantum fields dance and sway, stretching and vibrating, as if they are engaged in a cosmic ballet. They flirt with uncertainty, momentarily borrowing energy from the very fabric of existence itself. But don't be fooled, this isn't a mere magic trick of particles appearing from nowhere. Instead, it reveals a restless vacuum, a stage where gravity plays its disruptive role, sending ripples through the very essence of space. What secrets lie within this restless void? The answers beckon, tantalizingly close, yet just out of reach, inviting us to delve deeper into the mysteries of the universe. So let's dig deeper. Here's the key insight behind Hawking radiation. In curved space-time, particles are not absolute objects. They depend on the observer. In quantum field theory, what we call a particle is really just a vibration of a field. And whether a vibration counts as a particle depends on how you slice time. In flat space, everyone agrees on time, so everyone agrees on what counts as empty space. But near a black hole, time is violently distorted. Clocks close to the event horizon tick incredibly slowly compared to clocks far away. Because of that, the quantum vacuum near the horizon is defined using a different notion of time than the vacuum seen by a distant observer. That mismatch matters. A state that looks like perfect emptiness near the horizon does not look empty when described using the time of a distant observer. When you translate between those two descriptions, part of what was vacuum turns into real particle excitations. Those particles are what we call Hawking radiation. Nothing escapes from inside the black hole. The radiation is created outside the horizon, by gravity reshaping the quantum vacuum itself. Gravity doesn't just bend space. It bends time so strongly that even the definition of a particle breaks down. Hawking calculated the result of that distortion. Black holes have a temperature, and it's inversely proportional to mass. The bigger the black hole, the colder it is. The smaller it gets, the hotter it becomes. That single equation tells the entire story. Black holes aren't eternal. They behave like thermal objects. They glow. Hawking radiation does not mean particles escape from inside the black hole. Nothing ever crosses the event horizon outward. The radiation originates just outside the horizon, from quantum fields distorted by extreme gravity and time dilation. The horizon remains a one-way boundary, but the vacuum outside it does not remain silent. So why haven't we observed Hawking radiation directly? Because real black holes are enormous, and enormous black holes are extremely cold, colder than the cosmic microwave background. They absorb more energy from the universe than they emit. For now, Hawking radiation is drowned out by cosmic heat. Hawking radiation looks thermal, random, featureless, but that creates a problem. If a black hole evaporates completely, what happens to the information about everything that fell in? Quantum mechanics says information cannot be destroyed. This conflict sparked decades of debate. Black hole entropy, holography, and radical ideas about how space-time itself stores information. Hawking radiation sits at the intersection of quantum physics, gravity, and thermodynamics. It tells us the darkest objects in the universe still glow, and over long enough time, even black holes fade away. But one mystery remains. If black holes evaporate, does information disappear, or is it somehow preserved? Comment what you think about the information paradox.